Okay, we're going to talk about Mercury's orbit, and basically any particle's mass. The problem applies to the geodesic of a particle's mass in the Schwarzschild space-time. Under Newtonian 1/r force attraction, a planet follows a close elliptic orbit. That's an orbit with its axis, major and minor axis, fixed in space. However, perturbation due to the presence of other planets or astronomical objects leads to a trajectory that is no longer closed. Since the perturbation is small, such a deviation it will go like this. It doesn't come back to it's the same perihelion position, and described as elliptic order with precession axis or equivalent of precession of perihelion. That's why this problem is called precession of perihelion with Mercury. Uh, for case Mercury, after the perturbation by other known planet has been uh, calculated, there was still a discrepancy of 43 arcsecond per century, a very small amount. But following the similar situation involved Uranus, that eventually led to the prediction and discovery of outer planet Neptune in 1846. So to solve the Mercury discrepancy, a new planet, Vulcan, was postulated to lie inside the Mercury's orbit, but it was never found. And Einstein solved this perihelion precession problem by applying his new theory of gravitation, as we shall presently see. GR implies a small correction to the 1/r square force, which just brings about the 43 arcsecond per century advance in Mercury's orbit. Exactly. We talked the geodesic equation for and from the derived orbit equations. Particle motion in curved space-time, for example, the Schwarzschild space-time, is fixed by GR equation motion, the geodesic equation, which tells us how test particle move in the field. The geodesic equation can be viewed as Euler-Lagrangian equation. This with a Lagrangian equal to g mu nu x dot mu x dot nu. X dot, remember, is different respect to the curve parameter. Now, since we know the metric for this for the spherical symmetric case is the Schwarzschild metric, we're substituting, and also we take theta equal to 90 degrees, just a plane, and then this Lagrangian becomes this g00 term, ct dot, because x dot here, and grr, 1/, inverse of the g00 term, and r dot squared, and then there's also theta equal to r squared sine theta equal to 90 degrees, so it's just r squared, phi dot squared. So that's the Lagrangian for the geodesic equation. In principle, we could obtain the orbit, which is basically a function of r in terms of the orbit angle, by solving the geodesic equation. But this involves second order time derivative. So it's simpler if we proceed instead of the geodesic itself, but using the energy balance equation, which turns out only the first derivative. By energy balance, you simply kinetic energy plus potential energy equal to total energy equation. Recall, we use the same approach in the familiar Newtonian central force problem. We don't usually solve the F equal to ma equation. We solve using the energy balance equation to proceed. Turns out this energy balance equation in GR is just a covariant normalization condition for the Lagrangian. So Lagrangian is equal to minus c squared. Now, to understand this Lagrangian equal to minus c squared, remember, if we take the curve parameter to the proper time, then x dot simply is the full velocity. And so this full velocity, so therefore this is square the magnitude of full velocity, which we learn in special relativity is minus c squared. Okay, when we're talking for velocity. But you say, well, that's true for special relativity. How do we know it's still true in general relativity? Well, actually, it's also true in general relativity because you just take the basic uh, metric equation, which is s ds squared equals g mu dx nu. But ds squared is related directly to proper time minus c squared d proper time squared. Then you divide both sides of this equation by proper time squared, so minus c squared. This divide this equal to x dot, and this divide this by so, so that's just L. So L equal to minus c squared. So therefore, we have the orbital equation, just this expression for Lagrangian equal to minus c squared. And of course, this Euler-Lagrange equation. If we substitute the constant of motion, means those constants which are conserved quantities along the particle path, to rewrite this equation, just substitute the various. Now, what is the constant motion? If a metric or the field g mu nu is independent of a particular coordinate, let's say x alpha, okay. Now, for a particular alpha, not collection for x1, x2, x3, rather it's a particular x component. Then this dx d alpha is equal to 0 because it's independent. L is independent of that. And so the left hand side equals 0. So I have the right hand side must equal 0, which can be interpreted as a conservation condition, saying that this kind of dl dx dot is differential respect to proper time equals 0. So it does not change with time. So it's a conserved, it's a constant motion along the path because you're right using the geodesic equation. Now, our Lagrange, in our case, does not depends on t or phi. There's no t dependent. There's t dot, r dot, but phi dot, but there's no t and alpha. So L is independent t and phi. So there are two constants of motion. Okay. The first one is independence of t, means the conservation of 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 the differential L with respect to x dot 0. Okay, and the L is equal to g mu nu x dot. So therefore, you differentiate this, you find that it's just only g00 x naught dot. Okay. Which will, let's call this quantity kappa, defines minus this is equal to kappa. And then since the Schwarzschild metric element, so this is 1 minus r star over r cd dot is the kappa, which is the constant motion because Lagrange is independent of time. Same way, the Lagrange is independent of the azimuthal angle, and so therefore it implies the conservation of the g phi of phi dot. And so we're going to multiply by m. We call this quantity L to be the constant motion. Now, what is this L? Clearly, because this g phi is just r squared, so this is m times r times phi dot. So that's the momentum, the tangential momentum, and then multiply L. So this is just the r cross p. So therefore, this is just orbital angle momentum. That's why it's conserved. Okay. Now, what about kappa? So this is orbital angle momentum. Understand? Kappa actually is just particle energy, right, in units of mc. Remember, how do we define its energy? It's something that's conserved and in the appropriate limit reduced to something we associate with energy. That's how, in fact, we find energy expression in special relativity. And but in general, the same way. Okay. Now we know this is conserved quantity, but also we show this quantity reduced to the expression for energy in the special relativity limit. So therefore, this must be the expression for energy in the general relativity. The expression for special relativity is E over m squared c dot is the differential of coordinate time with respect to proper time. And but this expression because gr reduce special relativity when the r star equals 0, and indeed kappa reduced c t dot. That's the expression for energy in special order. So therefore, it's proper to associate kappa as the energy of particle in GR. So that's why it's also not surprising as conserved. So now we substitute this expression from kappa and L into the this L equal to minus c squared. We get this expression. This is kappa, and this is not changed, and the phi dot here is just L over mr squared. So this we claim this could be associated with energy balance equation, but anyway, this came from L equal to minus c squared equation. Now, if we multiply by this factor here, okay, the first term becomes this term, just get rid of this, and multiply m over 2. And the second term also same way, 1/2 m of r dot square. And then multiply this 1 minus, so this is just this term, and there's 1 power m cancel, there's factor 2. And this is just this factor here, multiplied c squared. Okay. And then we also use the fact r star is 2gm over c squared. Now we can, so this is just this term, this is just this term here. Now this this minus minus become plus 2 cancel, so g small m multiplied big M over r, this plus sign here, then move to become minus sign on the left hand side, and move this one to the right hand side, so this one and plus m. Okay, so but now we're going to call the right hand side, we just call this script e. So the script e over m is simple kappa squared minus c squared over 2. Okay, so therefore we have this equation here. Now this equation, except for this factor here, this r squared, is simply is the energy balance equation in the non-relative central force problem, because this is just the radial kinetic energy, this rotational, this angular momentum square of 2mr squared. This is just like a linear momentum. This can be written as p squared over 2m, and rotational, just rotational angular momentum squared divided by the 2 times the moment inertia, which is mr squared. So this is the rotation kinetic energy term. This, of course, is the potential energy term. So therefore, kinetic energy plus potential, and so this script E is identified as the total Newtonian energy. Now, what's extra is this term here, okay? The proportional to the Schwarzschild radius. This term will write out this. You know, this is just some factors 1 over r cubed. So we can think of this as a GR correction to the Newtonian potential for 1 over r to the 4th type of force. Okay, there's just the extra force factor coming from GR. So now we're going to go from the energy balance equation to the orbit equation to solve for the orbit of the planet. We follow exactly the same procedure as you do in mechanics course for the central force problem. Okay, first of all, because the orbital angular momentum is related to d phi d tau this way, so therefore d tau can be related to, because L is constant, is to d phi. And in fact, we're going to often replace the d tau by differentiate back to the orbital angle. Okay, and also instead of working with r, we work with 1 over r. Turns out it's much easier if you do that. We call that u. So differential u is back to the orbital angle. We call u prime is equal to just 1 over r square differentiate. Okay, and then du is so just replace the u by from these relations, and then replacing the d phi by d tau. So therefore, I get r dot terms. R dot is dr over d tau. So I know expression for u prime, and then turns out this you can just r dot. So r dot squares. So u prime square. This term gives me u square because 1 over r squared becomes u square, and this 1 over r term just reports to u, and the gr term turns out to be proportional r to 1 over r cubed. So therefore, I get u cubed and some constant. That doesn't matter. Okay, and we can work out alpha is equal to L squared GM. This this this, this alpha term is. Now we can solve this equation, which is the GR orbit equation, by perturbation. And we assume the u can be written as a 0th order term plus a small correction. This u1 is a correction of the order of r star. Okay, so therefore for the 0th order term, we assume that r star is not there. So u naught just u naught prime square u naught square minus 2 over u. So this is just some constant. Okay. Now we're going to solve this 0th order by differentiating respect to phi. So and then divide by 2u dot prime. So this becomes second derivative, and this will become first derivative. And it turns out every term is proportional to u naught prime, so that's canceled out. So you get this expression. So you notice this is secondary to something. Okay, so in fact you can view this equation as a simple harmonic oscillator equation. Remember, harmonic oscillator secondary is with time equal to minus of the spring force is minus omega x. In this case, x is u naught minus 1 over alpha. This is our x, and instead of differentiating with time, we differentiate with the angle. It's the same thing. And also omega, the frequency is actually 1 because I have exactly minus this, no other factor here. So therefore the solution to simple harmonic oscillator is just x some constant cosine omega t. Omega is 1, so therefore this cosine t become phi. So that's the solution to this equation here, this orbit equation for the 0th order term. And then if you put u equal to 1 over r, and these two both have 1 over alpha, combined give you 1 plus cosine phi, and you just flip from 1 over r to r, so you get this equation. And you recognize this is just the famous conic section solution. Okay, so it just gives you an elliptical orbit. Okay, and the eccentricity, this which appears as constant in the solution here, is identified with the perihelion, which is a shorter distance at phi equals 0. When phi equals 0, cosine equal to 1, so alpha 1 that's equal to the minimum value. And okay, when phi not equal to 0, this thing is smaller, so r getting bigger, so you trace out an ellipse. And it's clearly a closed orbit because phi going from 0 to 2 pi comes back to self. It comes back to r equal to r mean. So this is a closed orbit equation. So again, so for the unperturbed solution, you have this expression for the orbit equation, r phi, and it's a closed elliptic orbit. Now we're going to include the perturbation at u1 term. And the solution is straightforward, but it's a lot tedious, and you can find all details in box 6.4 in the textbook. Okay, basically what it is, instead of cosine phi, in front of phi is 1 replaced by 1 minus epsilon. Epsilon is related again to the Schwarzschild radius. Okay, and this will lead to a orbit, a precession orbit. Okay, which will or it's not close, and it's precession, and we'll talk about this in the next part of this lecture. What is this presence term? What does it mean?